Yesterday, I told you some general framework of topological twisting. And so I would like to point out at the beginning today that something special happens about the case when the dimension, complex dimension of Calabi-Yau is 3. Okay? So there are various ways to see it, but one is to look at the zero mode of fermion. So in the target space, we have a metric. And, but suppose the size of Calabi-Yau is large, so you can do some perturbative computation. In the limit when the Calabi-Yau is infinite and the curvature is infinitely flat, then you can do free field approximation. And then in our notation yesterday, for example, psi I has dimension 0, 0 operator on the world sheet. So that means that if the dimension of Calabi-Yau is n, then the number of zero mode would be n, because there is a constant solution on Riemann surface for each direction in Calabi-Yau manifold. On the other hand, psi I bar, so I and I bar goes from 1 to n, would be 1, 0 form. So on the surface of genus G, the number of zero mode for 1, 0 mode, the 1, 0 form would be G. So therefore, the number of zero mode would be n times G. Okay? So in general, if the surface is curved, the target space Calabi-Yau is curved, then this zero mode will be lifted because there are no translational invariants anymore in the target space. But the difference is some kind of index, so that's going to be preserved. So therefore, the zero mode difference, which is 1 minus G times n, still stays even if the target space Calabi-Yau geometry is curved. And this difference does not go out. So that's going to be important. So, so in the following, I'm going to use the A model notation. For now, so that the BRST charge that I introduced yesterday takes the form of integral of G plus the left moving supercharge and the right moving supercharge like this. Excuse me. So I said that when the dimension of Calabi-Yau is 3, something special happens. And one thing that is special is that in this case, this number of zero mode difference is going to be 3 minus 3G. So you have total net amount of zero mode number difference of this amount. So because of this, you can insert 3G minus 3 of these supercharges for the left mover, and the same amount for the right mover. And this turned out to be non-zero because this exactly soaks up the zero mode. For example, I remind you, G minus is Gij bar, psi j bar, del of xi. So this soaks up exactly the right number of zero mode. And what's special about this is that this turned out to give you the measure on the moduli space of genus G Riemann surface. So this is something that you can integrate over the moduli space. So just to explain why that is, I just want to remind you that if you have a moduli space, you can consider tangent space to it. Tangent space is the complex structure of the moduli space of complex structure. And just like we discussed in the case of Calabi-Yau yesterday, this is the same as the space of 0, 1 form with value in holomorphic component of the tangent space, whose element is a Beltrami differential. Okay? So if you have something like that, then you can integrate this with G minus. Okay? And then you get some kind of number out of it. Now, there is an ambiguity in the choice of basis of Beltrami differential because you can change the Beltrami differential by the amount which is total derivative. But this won't change under this shift because del bar of G minus is 0. So that means that this type of coupling is a well-defined coupling between this integrand and element of the tangent space to the moduli space. And you have 3g minus 3 of them for the left mover and 3g minus 3 of them for the right mover. And so these are linear functions for each of these directions. And you have a maximum amount possible. And moreover, these are fermionic, so these are antisymmetric. So what this is saying is that this thing is a top form on the moduli space of genus G Riemann surface. So this is something that you can integrate. So the definition of therefore genus G topological string amplitude is simply the integral of this top form on the moduli space of Riemann surface. So you consider genus G Riemann surface, and you consider all possible shapes, and you integrate this. Okay? So you can think of this as a two-dimensional sigma model with Calabi-Yau target space coupled to two-dimensional gravity. Now, if you have topological field theory, in general, you can consider coupling it to topological gravity in 2 dimensions. And it turns out that when the dimension of the target space Calabi-Yau is 3, that coupling becomes particularly simple and gives you this plane integral over the moduli space. So this is some special feature of Calabi-Yau threefold. And it turns out that this is also the case that is of interest for application to superstring theory, which I will discuss later. I'm not sure whether I get to that today, but I hope to get to that. And I understand Edward Witten will say something about it later today, so this will be a good segue to his talk also. I just want to mention one small comment. I want to make one small comment, which is that the case of G equal 1 is somewhat special. In this case, we say that moduli space of complex dimension of the moduli space of genus 1 surface is 1, which most of you are familiar with in terms of this fundamental domain of modulus of torus. Oh, this is in the, I believe I'm using this notation where the supercharge is in this notation. This is in the I was using this notation where supercharge is G plus and G bar plus. In this case, I'm using the opposite supercharges, whatever the choice of basis you are choosing. Okay? So in this case, dimension is 1, so one may naturally try to consider integral of something like this. But it turns out that this gives you 0. Because on torus, actually, the net number of supercharge is equal to 0. So net number of fermionic 0 mode is 0. And the reason for that is actually the moduli space of torus with no puncture is actually not quite well defined, not quite stable. You have to put actually one puncture to it. So the better defined object is given by inserting one marginal operator to it, and then integrating G bar and G bar minus over it, over moduli space of Riemann surface with one puncture. It turns out to be expressed as a derivative of some well-defined function on the moduli space of Calabi-Yau manifold with respect to the marginal deformation parameter TA that I introduced yesterday. And this F1 then is expressed as integral of 2-point function of U1 current integrated over the moduli space of torus with one puncture. In the case of genus 0, you consider 3-point function. Oops, maybe I should have moved this up. In the case of genus 0, what you can do is consider 3-point function. In this case, you consider, say, marginal operator and 3 of them. So you consider now genus 0 means that you are considering sphere and you consider a sphere with 3 punctures. And this marginal operator phi A, in the case of A model, can be expressed in this way. In the notation I introduced yesterday, where Ka is an element of H11 corresponding to the marginal deformation of the scalar structure. It turns out that this CABC can be expressed as derivative of some holomorphic object, which I'm going to call as genus 0 topological string partition function. And in the literature of supersymmetry, X0 is what is called a prepotential. And in fact, I hope I will get to that tomorrow, but in appropriate limit of Calabi-Yau compactification, the low energy dynamics becomes n equal to gauge theory. And in that case, F0 is related to so-called Seiberg-Witten solution to the prepotential, which I hope to get to. And then relation, so I hope to describe the relation between this type of computation, geometry of Calabi-Yau, and the Seiberg-Witten solution to the supersymmetric gauge theories. Okay? Now, so these are the objects that we can consider computing in topological string theory. And so I would like to describe method to compute these quantities and later discuss meaning of these quantities in the context of type 2 superstring compactified on Calabi-Yau manifold. But before we get to that, it's useful to understand a little bit more about the space on which we are evaluating these quantities. These quantities are functions. For each Calabi-Yau manifold, we can compute this function. But Calabi-Yau comes with family. There is a moduli space to Calabi-Yau, both in terms of complex structure and scalar structure. As I said yesterday, the Yau's theorem guarantees that for each scalar structure and complex structure, there is a unique Calabi-Yau manifold. So therefore, these objects are all function or section of appropriate bundle of a moduli space of these spaces. So it will be useful to understand the structure of these spaces first. So that's the next section, the moduli space of Calabi-Yau compactification. Now, let us first review the moduli space of complex structure. Of the Calabi-Yau manifold M. And this is, as I explained yesterday, is a moduli space of B model. And in this case, we can actually borrow the result of mathematics because the B model observables are independent of the size of Calabi-Yau manifold. It's independent of the scalar structure. So you can take the size of Calabi-Yau very large. So then the leading order result by alpha, in the alpha prime expansion becomes exact. And moreover, as I said yesterday, the BRST invariant configuration of the sigma model variable is actually a constant map. So that means that the physical object you can compute in B model will be just plain integral in the target space Calabi-Yau manifold. So all this suggests that actually the structure, moduli space of complex structure, you can understand from purely classical geometric point of view. This is not the case in the case of A model, and the scalar moduli space will receive quantum corrections. So that has more interesting structure, but it's easier to understand the B model case. So let me first discuss that. So to describe MC, it's useful to understand that actually the essence of complex structure in the Calabi-Yau space is captured by holomorphic 3 form. So there is a unique, nowhere vanishing 3 form on the Calabi-Yau space. So there is a unique one, but normalization of that is not unique, obviously. You can multiply some complex constant to it, and it's still holomorphic. So that means that for given Calabi-Yau, there is a unique holomorphic 3 form up to overall scaling. So this indicates that there is a natural line bundle over moduli space of complex structure of Calabi-Yau dictated by the holomorphic 3 form. In fact, this turned out to be, in a mathematical language, some sub-bundle of what is called Hodge bundle. And there is a natural metric for this line bundle, which is given by integral of omega wedge omega bar integrated over Calabi-Yau manifold. It turns out that this complex moduli space is scalar, and its metric is given by the curvature of this line bundle. That is, that if I define this as e to the k, then the metric on this moduli space is simply given in the standard way as you would if this k were a scalar potential for it. There is a minus sign here, I'm sorry. Okay? On this, when we're discussing moduli space, it's particularly useful to introduce what is called flat coordinate. These are the coordinates that naturally appears in the sigma model perturbation. Yesterday, we talked about deforming the worldsheet sigma model action by adding perturbation to it. Something like that. So there is a natural parameter that coupled to the marginal deformation. These flat coordinates are the ones that is directly related to these operators. Other coordinates can be non-linearly related to that. So I would like to describe that this, how to compute. I would like to tell you how to compute and derive flat coordinate in the case of complex structure moduli space. So to do that, I'm going to choose a basis alpha I, beta I of H3 of the Calabi-Yau target space. And the dimension of this space is 2H1, 2 plus 2. This also appeared in the talk by Martin. So, so that means that I goes from 0, 1, 2 to H2, 1. You have 2 alpha and beta, so overall, you have 2 times H1, 2 plus 2 of them. And I choose a basis so that they are orthogonal like this. Okay? So with this choice of H3, we can integrate over each of them. We can integrate holomorphic 3 form over each one of them. And so I define xi to be equal to integral of omega over this alpha cycle, and fi to be integral of same omega over beta cycle. Okay? These are called period integral. And the great thing about this is that these can often be computed very explicitly for given Calabi-Yau manifold. So this is sort of something that you learn in undergraduate course on mathematical physics, that you learn, for example, the solution to hypergeometric differential equation can be obtained as contour integral in complex plane. So this is sort of generalization of that in Calabi-Yau space. And so these actually obeys very often nice hypergeometric type differential equation. So you can solve that to compute them explicitly. And there is another thing that helps, and that's the reason actually why we are considering this holomorphic 3 form, is that there is some kind of theorem that is actually generalization or a variation of a so-called Torelli type theorem that says that complex structure of M is specified by xi's. So if you know the integral or period integral of holomorphic 3 form on alpha cycle, that specifies the complex structure. For example, if you have taken if you have studied the perturbative string computation, then you might have learned that if you know the period matrix of Riemann surface, that specifies the complex structure of the Riemann surface. So this is a generalization of that statement for Calabi-Yau manifold. So in particular, so that means that this Fi is determined by this x. But for example, there are various constraints. For example, if you rescale omega, x and f should scale in the same way. So that means that this f of x should be a homogeneous function of x of degree 1. It turns out that this f1, fi can also be written as derivative of, with respect to xi, of some universal function f naught. So this is a degree 1 function, so this f naught should be degree 2 function. And this turned out to be related to the prepotential that I was referring to earlier. So this is going to give you a prepotential. Okay? So the flat coordinates that I was referring to is basically the ratio of x. So as I said, x determines the complex structure, but there is a redundancy to description because you can rescale omega and you get the same complex structure. So basically you can take the ratio of them, you pick some particular direction you like to be x naught, and just take the ratio of that and then call that as TA. Okay? And very often you have a natural choice for x naught, and so that gives you the flat coordinates. So the flat coordinates that I'm going to be discussing, and the one that will appear in this kind of perturbation, is actually the ratio of these periods. So we can compute them very explicitly. And when we discuss mirror symmetry, mirror manifold, etc., then this flat coordinate becomes particularly important. Now, since this choice of coordinate xi depends on the choice of this basis of H3. So therefore, it's not a globally defined function on the moduli space. It depends on the choice of the basis. But there are quantities that you can compute that are globally defined in the moduli space of Calabi-Yau. So let me give you a couple of them. So for example, I define the prepotential over there. So I can take 3 derivatives of the prepotential. And that is actually, I just wrote it up there here. So that turned out to be this 3-point coupling that I defined over there. And this turned out to be a well-defined thing. So I say that this is a metric of some line bundle over the moduli space of Calabi-Yau manifold. And this is, therefore, the section of L squared wedged with symmetric product of cotangent space to the moduli space of Calabi-Yau manifold. We can write this thing also in terms of integral of holomorphic 3 form and 3 derivative of holomorphic 3 forms. So you see that in this case, we can compute these things quite explicitly. Another thing that you can compute quite explicitly is this metric and therefore scalar potential itself. So e to the minus k, as I just wrote over there, is I times omega, which omega bar integrated over Calabi-Yau manifold. But probably you might have seen when you study the perturbative string theory that if you have an integral like that of holomorphic and anti-holomorphic thing, you can decompose that to period integral. This is called Riemann bilinear identity. So we have a basis for H3 over here. So we can write this as an integral of omega in alpha cycle, omega bar in beta cycle, minus omega in beta cycle and omega bar in alpha cycle. So if I use this definition of period integral explicitly, therefore we can write this as xi fi bar minus xi bar fi. And I said that these period integral can be evaluated very explicitly by solving differential equation in many cases. So that means that metric and Calabi-Yau spaces are completely known. So these are a wonderful thing because as I told you yesterday, in compact Calabi-Yau manifold, the metric of the target space often are not known. And even if it is known, alpha prime correction on the worldsheet would correct it. And even if we knew corrected the metric, we don't know in general how to solve the two-dimensional sigma model. Nevertheless, we can compute the metric on the moduli space of those theories. So we can circumvent all these kind of difficulties. If you have, so this is a very special feature of the metric on the moduli space, and you can derive from these various identities. So for example, it's a very simple, straightforward algebraic exercise to show that if you have a metric, you can compute a Riemann curvature, and then there is actually identity between Riemann curvature and the metric. So this is a Riemann curvature on the moduli space of Calabi-Yau manifold, and it turns out to be simply expressed in terms of the three-point coupling and the metric itself. This is called special geometry relation, and in fact, geometry that has this kind of features called special geometry. And actually, these two are equivalent statements. If you have this type of metric, it's a simple algebraic exercise to show this, and I recommend you to do that if you have spare time. Or you can go backward. Okay? This special geometry relation can be derived in various different ways. So here, I derived this using the complex geometry of Calabi-Yau manifold, but you can also derive it by using the word identity of n equal 2 supersymmetry on the worldsheet. And these are called the TT star equation after Checotti and Buffer. You can also derive that from the target space point of view, because if you have a Calabi-Yau manifold compactification, you have n equal 2 supersymmetry in 4 dimensions. And a structure of the supersymmetry and supergravity in 4 dimensions dictate that the moduli space for the scalar field has to have this kind of structure. So you can derive it from this kind of perspective. So this shows that in the case of B model, we can just use classical geometry, but in the case of A model, there are quantum correction, but even with quantum correction, this type of feature still persists. So we can use similar kind of structure. So once we know the prepotential, once we know how to compute prepotential in A model, which would have quantum correction to it, you can still compute a metric on the moduli space of the quantum corrected A model. Okay, any question? Yes, please.
What causes the asymmetry in X and F?
Sorry?
As soon as there's an asymmetry in X and F.
Yeah, you can do symplectic transformation to mix them up. So that leads to different choice of coordinate. Okay? So now I'd like to, so this was the preparation for the rest of the talk. So I wanted to first tell you what is the space on which we are doing this type of computation. So the next step is actually to tell you what we are computing. With f of g. Okay? So I have already told you that in the case of, by the way, first I should tell you the following thing. So I'm going to tell you this for both A model and B model. And B models are easier to describe because these are rather classical objects. And A model contains quantum correction. And there have been several works on answering this type of question. So in the case of g equals 0, so I told you that I'm going to give you some references. So this is one of them. So there is a paper by Candelas et al. In nuclear physics, B3599121, which actually computed A model genus 0 answer explicitly for some class of Calabi-Yau manifold, and made some conjecture based on this computation about the structure of A model amplitude in general, which was later proven by Aspinwall and Morrison. And so that's CMP 151, 93, 245. And for genus is equal to 1, there is a paper by myself with Bershatsky and Chekoty buffer, which later I will refer to as BCOV1. And the archive number is 9302103. And then for genus greater than 1, there is a BCOV2, which is 9309140. Okay? So in the case of, so let's first describe the B model. Okay, so in the B model for genus 0, I have already told you that 3-point function is triple derivative of prepotential with respect to these three things. Okay, and so this is totally classical. And the reason for that, there are two reasons for that. One is that, as I said, BRC invariant configuration in B model is a constant map. So therefore, one should be able to write the answer in terms of purely as an integral over the target space Calabi-Yau. The answer should be independent of the Kähler metric, so that means that you can take the size of the target space Calabi-Yau to be large, which means that alpha prime is small relatively to the size of Calabi-Yau. So therefore, the leading order result of the sigma model in loop expansion should be exact. Okay? So this is the genus 0 result. Genus 1 case, so this is what we derived in this BCOV1 paper. The genus 1 partition function is not quite an integral in the target space because there is a subtle breaking of BRST invariance that I will tell you later. So rather than expressed as an integral in target space, it is actually given by determinant of Laplacian. So it is given by determinant of Laplace operator and compute log of that and sum them up appropriately. And that gives you a genus 1 amplitude, where this delta PQ is del bar dagger acting on the space on the holomorphic space of PQ form on the Calabi-Yau manifold. So it's not quite an integral in target space. It's computing one loop determinant. It turns out that this particular combination of determinant of Laplacian is a combination of so-called racing torsion. And the particular feature of this is that this combination is independent of the Kähler moduli. In general, the determinant of Laplacian would depend both on complex structure and Kähler structure. But it turns out that if you take this particular combination, the Kähler moduli dependence cancels out. Okay, so as I will tell you later, the answer should primarily should be holomorphic nominally. And in fact, if I take t derivative, the derivative of f1 with respect to holomorphic coordinate in the moduli space, you get almost a holomorphic thing as expected. But there is some subtle breaking, which I will discuss later. For genus greater than 1, there is a natural generalization of this kind of computation of determinant in terms of Feynman diagram. And so this can be regarded as quantization of complex structure of the moduli space in appropriate sense. And there is actually some recent interesting work by Costello and Lee clarifying the mathematical aspect of this kind of construction. But unfortunately, I do not have time to discuss that. So let me move on to the case of A model. So in the case of A model, the answer can get quantum correction. The kind of quantum correction we would get are the instanton corrections. The reason for that is actually I have already mentioned yesterday, the answer should be still almost holomorphic in the target space. So you have a T and T bar almost holomorphic in the moduli space of now Kähler structure. And in the Kähler moduli space, you have T coordinate and its complex conjugate T bar. And the independence on the T bar coordinate means that answer should be exact as sum over instantons. Instanton approximation becomes exact in evaluation of the A model amplitude. So that's what we will see now. So let's first discuss the G equal 0 case, the genus 0 case. So this is, as I said, something that was initially worked out by Candelas et al. Based on an example and proven by Aspinwall and Morrison. So in this case, the 3-point amplitude on genus 0 can be, first of all, expressed as an integral of triple product. So these K's are elements of H11, which correspond to the marginal deformation of this A model. So this will be the classical answer. So if you just do the classical answer, this would be get this. But then you get quantum correction by sum over instantons. Okay, so I have to tell you, explain the notation. This T is a flat coordinate in the Kähler moduli space. D is a degree of the instanton. So when you have an instanton, that means that you have a map from sphere to the target space. And that map should be holomorphic. So map being holomorphic in particular means that image is a minimal surface. So there must be a 2 cycle where the image wraps around. So that image can actually correspond to this TA, the direction of H11. So these D's are degree of this map, which means that it tells you the integral of the image. And so this D times T is basically just sum of DA, TA, right? So if you have just simply a sum of a map from Riemann's sphere to Calabi-Yau manifold, then you just have this map. But it turns out that if you have one such map, then you can wrap it around many times. So you have an effect of multi-covering. So what I said, conjectured by Candelas et al. Was that they guessed this type of structure for multi-covering, which was later proven by Aspinwall and Morrison. And this quantity here is related to so-called Gromov-Witten invariant. Related to so-called Gromov-Witten invariant corresponds for the genus 0 surface of degree D. We can go on to discuss genus 1 case. So genus 1 case is similar. So for genus 1, again, the nice thing to compute is a derivative with respect to one derivative with respect to the flat coordinate. The leading one is again classical, and I'm going to actually writing this for general Calabi-Yau. Maybe I'll just write the result for genus the Calabi-Yau threefold. In this case, the expression is simpler. So then we have TKA times C2. So this will be a classical answer. Yesterday, actually, somebody asked me, so yesterday, for example, I gave you a computation of Chern classes for quintic, and somebody asked you what's the use of C2. And this is where actually C2 appears. And then there are quantum corrections. So this is a number essentially of holomorphic map from worldsheet torus to the target space. The surprise was that there is an additional effect coming from sum over genus 0 holomorphic maps. So this will be this is a contribution from holomorphic map from genus 1 surface to the target space. That's why I have 1 and D here. But it turns out that there is some kind of degenerate holomorphic map where most of the worldsheet get mapped to actually the spherical geometry in the target space. And then there is a small bubbling of a handle. And this contribution turned out to be this kind of structure. So we had to take this into account in order to properly read off this genus 1 Gromov-Witten invariance. And for genus greater than 1, we have this kind of structure. So this is the Euler characteristic of target space Calabi-Yau. And then we have an integral over moduli space of genus G surface. And this is a Chern class of a particular line bundle called Hodge bundle over moduli space of Riemann surface. And then you have sum over genus G Gromov-Witten invariant. And then in addition, you have multi-covering plus bubbling. Multi-covering, something like this denominator formula, and bubbling, something like this for higher genus. And these invariants have been computed explicitly by mathematicians. It was also conjectured by Gopakma and Vafa earlier based on some computation of BRST, a number of BRST particles, which VPS particle, excuse me, and which probably Edward will talk about later today. But these are totally known. So it's kind of complicated. So I'm not going to write that. But these are totally expressed in terms of zeta function and Bernoulli number. So for example, for G equal 2, this term is given by chi over 5,760. And for G equal 3, it is given by chi over 1451520, etc. So these are totally explicitly computable. Okay? Now, how we go about computing these? So we can compute a leading term, but how we can go about computing these? Or better yet, get some kind of closed formula for that. So I'm going to show you one way of computing it, which is a holomorphic anomaly equation, which basically shows you how you can compute these explicitly for all G in the case of class of non-compact Calabi-Yau, and extremely high number of G for compact manifold. So holomorphic anomaly equation. Okay, so let's first consider a simpler example. So here I consider genus 1 amplitude like that. But in genus 1 case, it turns out that you can actually compute topological string amplitude for any dimension target space. In that case, you just replace this by n and this by appropriate power. Okay, so not appropriate power, excuse me, the appropriate degrees. Okay, so for example, let's consider the case when target space is torus, which is the simplest Calabi-Yau manifold you can think of. So let's consider this as a target. So you can have a parallelogram with size identified like that. This is a target space, not worldsheet. This is a target space. So tau is a complex structure, and T is a scalar structure which is related to the volume area of the torus. And then theta is a B field which wraps on this target space torus. There is a T duality transformation when the target space is torus, which basically exchanges tau parameter, and which is a complex structure, and T parameter, which is scalar moduli, which is an example of the mirror symmetry. Oops, maybe I shouldn't do too much complicated thing. Okay, so we can actually compute in this case F1 completely explicitly because this is a free field theory. So basically the answer is theta function. So let me show you the answer. Sorry. This was to wake some of you up. So I show that torus is parameterized by target space torus is parameterized by t and tau, and we can compute that explicitly. The F1 we can compute F1 explicitly, and it is given by product of Dedekind eta function, which I hope you are familiar with for t and tau. And I said there is a mirror symmetry, so the answer should be symmetric on the exchange of t and tau. But there is some kind of surprise because eta function is not totally modular invariant. You have to provide something non-holomorphic to make it modular invariant. So you actually get something non-holomorphic. So for example, therefore, if I compute derivative of F1 with respect to t, which you'd expect the answer to be holomorphic, it turns out that you get some non-holomorphic piece to it. And then you get some constant. And then you get sum over instantons. In this case, actually, sum over SL2Z matrix with determinant in the exponential. Oh, I shouldn't write it over here, but some of you sitting over there won't be able to read it. So I'm going to transcribe it over here. So you have a sum over SL2Z matrix of e to the 2 pi I determinant of m times t. So this 1 over 24 is this one right here. And this term is sum over instanton here. In this case, there are no multi-covering, no bubbling effect. But there is this funny piece over here, which is consequence of this term here. You have a question?
Yeah. Is it a sum of the A model and B model X?
This is sum of A model and B model here. But if I take derivative with respect to t, which is well defined in A model, this entire piece drops out.
Why does it make sense to consider a sum of A model and B model answer?
I'm just, well, because for both, so if you remember the definition of F1, which is somewhere there, but I erased it, I guess. So then F1 is just an integral of j bar over moduli space of torus. This does not discriminate A model and B model. The other way of saying it is that in order to define A model and B model, we twisted the worldsheet. But twisting refers to the choice of curvature. So you need a curvature to make a differentiate because well, in the case of when the worldsheet is torus, the worldsheet is flat, so you don't have to actually twist to get A model or B model. So in some sense, the A model and B models are treated equally in the case of torus. Worldsheet torus. And in fact, this is a definition. This does not discriminate A model to B model. So that's why the answer F1 turned out to be sum over A model answer and B model answer. But actually, the topological string, more well-defined object is F derivative with respect to t, which is related to the torus with one puncture. And that is almost given by holomorphic object on the Kähler moduli space, except for this anomalous piece. Okay? And this is related to, in the case of B model, so-called Quillen anomaly. So I remind you that in the case of B model, so this was A model, but in the case of B model, in general, F1 is given by sum of determinant of Laplace operator. This is acting on the PQ space of PQ form. And there is a notion called Quillen anomaly. That says that for certain combination of determinant of Laplacian, you can consider that as there is a certain line bundle associated to it. And del del Burr compute the curvature of that space. So del del Burr of F1 in general is not equal to 0, but it is related to the curvature. But this space in this case is scalar. So this curvature is computed as del del Burr of log of some object like determinant or metric or something like that. So this actually enables us to actually integrate this thing. So in the case of B model for Calabi-Yau space, for example, it turns out that we can integrate this Quillen anomaly to write F1 as log of e to the h21 plus 3 over chi over 12, excuse me, times the scalar potential on the Calabi-Yau moduli space divided by the determinant of the metric on the Calabi-Yau moduli space times something which depends totally holomorphically on absolute value of some holomorphic object. So this is the holomorphic. So modulo this quantity, and I showed you over there, here, for example, that you can compute scalar potential and the metric totally explicitly for given Calabi-Yau manifold. And modulo this piece, you just have holomorphic data. So you just need to fix this holomorphic part to compute F1 exactly. And we can do that, in fact. So let me give you an example. So I told you an example of quintic yesterday. And you remember the computation of total Chern class of this space, which is given by 1 plus 10j square minus 40j cube. The term linear in j is missing. This is because this is the Calabi-Yau space, so the first Chern class is 0. And from that, I derived that the Euler character, namely the integral of C3, is minus 200. But now, in the case of Calabi-Yau, where chi in general is sum over pq of minus p plus q of hpq. So in the Calabi-Yau case, it turns out this is equal to twice of h21 minus h11. And we know this answer is minus 200. But we also know in the case of quintic, what is h21? Because well, H21 is a complex moduli space, which is basically the way you can deform this quintic polynomial by adding any degree 5 monomial to it. So you just need to count the number of monomial of degree 5, and it's a very simple exercise to do that. So basically, the possible monomials are this combinatorial factor, but there is a change of coordinates that you have to subtract, and this turned out to be 101. So we know H21 is 101. So this means that H11 is 1. So this is an example which is actually good to compute the A model amplitude because the moduli space is one-dimensional. So it's relatively simple. And moreover, in this case, the mirror manifold is known. So remind you that a pair of Calabi-Yau manifold is called a mirror pair if the A model on one Calabi-Yau is equivalent as a quantum theory to B model on the other Calabi-Yau. So I'm going to tell you the mirror of this quintic surface. She was first derived by Brian Greene and Ronen Plesser. So the quintic has G5 to the cube symmetry to it, basically rotating each one of the coordinates by a fifth root of unity. But there is an overall coordinate change, etc., so we ignore that. Then there is a G5 to the cube symmetry. So you can consider orbifoldizing the space with respect to that. So this is what Brian Greene and Plesser considered. And you can look at that in nuclear physics B338-9015. And so this exactly gives you manifold with H11 is equal to 101 and H21 is 1. So the role of H11 and H21 is reversed. So A model and B model is reversed. And they have actually a quantum field theory derivation of why these two are equivalent. And so if I call this space as MT, with this T, this single scalar parameter, then there is a mirror to this space, which is given by this equation. Okay? So it turns out that if you require this kind of symmetry, then this is the only perturbation you can make. And this is consistent with the fact that H21 is 1, so that you just have one complex parameter, moduli parameter to it. So there is a map between that scalar moduli T and this complex structure parameter psi. The question then is how to derive the relation between them. So this was worked out by Candelas et al. Paper that I mentioned over here. So the idea was to use the flat coordinate, because flat coordinate is the one that couples linearly to perturbation. That should be the same for A model and its mirror B model. So if you compute the flat coordinates, then you can understand the mirror map. And therefore, the mirror map should be T is equal to the ratio of the period. So if you have an equation like that, it's a well-defined mathematical task to compute the period integral of a homomorphic three-form and just solving the hypergeometric type differential equation. And they take the ratio of the two solutions, and that gives you the flat coordinate. And so this gives you a nice illustration of how actually you can compute F1 and higher genus amplitude explicitly. So you have a differential equation for F1, which is somewhere up here. So you have a del del bar is equal to curvature, and you have derived this expression. There is an ambiguity in holomorphic object. But great thing about holomorphic object is that if you know the boundary condition, often you can determine holomorphic object uniquely. So I need to provide boundary condition. And we can provide boundary condition because for t goes to infinity, we have a large volume limit, so we know how to evaluate it. In this case, we know that F1 should behave like 25, 12. Well, if I take derivative with respect to t, it should go like that, just come from this coefficient right here. So we can compute this thing. And then we can require that the answer should be regular at psi equals 0, which is because psi equals 0 is just the original quintic. And this totally determines f to be psi to 62 over 3, 1 minus psi 5. And this completes the computation of genus 1 topological string amplitude. And from that, for example, you can deduce the genus 1 Gromov-Witten invariant. And the first few of them were computed by mathematicians, and they showed complete agreement. We can go on to compute higher genus amplitude. So how do I do that? So that's the focus of the holomorphic anomaly equation. So I remind you that Fg is given by integral of this thing over moduli space of Riemann surface. Now, if I suppose compute derivative with respect to anti-holomorphic parameter of the moduli space, because I want to find some subtle breaking of holomorphicity, just like Quirin's anomaly. So, well, anti-holomorphic derivative would bring down BRST trivial operator like this, integrated over Riemann surface. So if we are computing BRST invariant computation, then this BRST operator, you can just move outside of Riemann surface and show that this vanishes. So that will be a holomorphicity. However, G plus and G minus does not quite commute, but gives you the twisted energy momentum tensor. And the insertion of that energy momentum tensor deforms the wall sheet geometry because the energy momentum tensor are coupled to the metric on the Riemann surface. So what you get is a total derivative on the moduli space of Riemann surface. And if you have total derivative, you can just go to the boundary of moduli space and evaluate it. So that gives you an answer. So that gives you this type of equation. So I can draw that pictorially because it is a little bit hard to look. So what this equation means is that if you have a genus G surface, and then you integrate over moduli space of this surface to compute the string amplitude, I compute the anti-holomorphic derivative with respect to that, and it turned out to be given by two contributions. One is that the genus G minus 1 surface with 1 point inserted, or 2 point inserted, because I'm taking two derivative over here. And that is, maybe I should draw it over here. So one contribution is genus G minus 1 surface with two punctures with A bar attached to it. And the other contribution is genus R surface and genus G minus R surface connected by 3-point amplitude with A bar in it. So these are these two terms. Okay? So you can see that this is a recursive relation in genus. So in principle, you can try to sum them up. By the way, the Quirin anomaly is an example of this equation too. So we can write the Quirin anomaly in a similar fashion. So Quirin anomaly had to do with one loop amplitude, torus amplitude with 1 point attached to it. And then suppose I take derivative with respect to it. Then you get two types of contribution. One is sphere connected, in this way. And the other is connected in this way. So you can actually derive Quirin's anomaly from point of view of topological string in this way. Now this type of equation looks suspiciously similar in structure to the recursion relation that Nima Al-Kani-Hamed discussed in his lecture. So I'm actually quite curious to understand whether there are any connections between them. And so, but the point I wanted to make is that these equations have such nice structure, so you can actually integrate that iteratively. You can solve that iteratively, genus by genus. And this is not just the statement, you can actually do that in practice. So this is actually one of the things we did in this BCOB2 paper. We gave a precise way that you can actually integrate this recursive relation, order by genus by genus, and using some formula which looks like Feynman diagrams. And this turned out to be actually quite practical. So it turns out that you can actually use this formula to compute f of g to all order in G for a class of Calabi-Yau manifold, non-compact Calabi-Yau manifold called quintic. So I have to tell you what kind of boundary condition you choose. So for t goes to infinity, you choose a boundary condition that fg goes to this type of integral that I mentioned earlier. I wrote somewhere up there. So this is one boundary condition. And the second type of boundary condition is regularity. On the moduli space of Calabi-Yau, for example, psi equals 0 at quintic. And the third is a conifold behavior. Which is that fg has some kind of singularity if you go to the conifold point, which example of which I will tell you later. But this is some example of singularity of Calabi-Yau space. And t is a coordinate that is sort of normal to the conifold. And if you impose these conditions, then it turns out that for toric Calabi-Yau manifold, which I'm going to tell you just after this, you can determine f of g to all order in G. So obtain f of g for all G for toric. And but it's more interesting if we can understand compact Calabi-Yau manifold. And for compact Calabi-Yau manifold, it turns out that the situation is more difficult. And right now, at this moment, we don't have a method of actually computing f of g to all order. The state of art is by Huang et al. 0612125. And in this paper, they use these three conditions and the holomorphic anomaly equations to compute f of g for quintic. And they found that you can actually determine it up to from g equal 1 to 51. And for now, 51 is as high as you can possibly go. And in order to go higher, look like you need to know a little bit better about the boundary condition. And that may be doable, and so that would be very interesting to do. And especially because actually I think that in the compact case, understanding the large G behavior for asymptotically large G would be very interesting for various reasons. So for example, if I have time, I would like to discuss the relation of f of g to computation of entropy of black holes, etc. And there actually understanding f of g for large G for compact cases would be very important. Okay, so I believe I have about 23 minutes or 22 minutes. So I have two more topics I hope to cover, and I hope to cover at least one of them. And one is a non-compact Calabi-Yau manifold. Yes? Yeah. Sorry? Yeah. SL2Z, yeah. Oh, I'm sorry. Okay, yeah, that's right. Yeah, this must have been GL2. Actually, yeah, so sorry. That was a typo. Okay, so now the reason I'm going to tell you about non-compact cases is that over the last 15 years or so, remarkable progress has been made in non-compact cases and with or without D-branes. And so this will lead us to some of the discussion we'll have later. So just let me give you a few examples of non-compact Calabi-Yau manifold. So what I would like to tell you with an example of so-called local CP2 first. So CP2 is, of course, not Calabi-Yau. The first Chern class is non-zero. But you can make this to be Calabi-Yau by considering line bundle over CP2, and so that the first Chern class of the fiber cancels that of the base. So more explicitly, the way you do it is to start with the C4 with origin removed, for example, and you consider the following kind of identity equivalence. Where lambda is some complex number. So you consider this kind of equivalence and divide this space by this equivalence. Clearly, you see that in the locus when x equals 0, this is just original CP2. So therefore, adding x1 gives you the fiber direction to it. Okay? So this will give you a line bundle, which is often denoted by in this way. So basically, you have a line bundle with appropriate first Chern class, so that the total Chern class is going to be 0. So this describes the geometry of Calabi-Yau. This is the Calabi-Yau space, so you can actually put the Calabi-Yau metric on it. And you can also think of this as a limit of non-compact compact Calabi-Yau, where you have 4 cycle, which is CP2, and the geometry near that CP2 is modeled by this geometry. Another geometry that that's often show up in this kind of literature is a resolved conifold. And so that is similar in spirit, but now identification will be like that. So the powers are different. Okay? And this will give you O minus 1 plus O minus 1 over CP1. So this is going to give, this is an example of geometry near CP1. Later we will encounter another way to resolve the singularity of this space called deformed Calabi-Yau, deformed conifold. Which is given by this equation. Where y is an element of C4. So if mu is real, well, it's convenient to write yi as a in terms of real part and imaginary part. Then this equation can be expressed in terms of real coordinates as xi square minus pi square is equal to mu. And suppose mu is real and positive. Then you see that the other equation is xi pi is equal to 0. Then you see that when at the locus when p is equal to 0, this is just a 3-sphere. And it turns out that if you add p direction, it is just a total space of cotangent bundle over S3, which is also an example of Calabi-Yau space. So you can think of p equals 0 locus as a sort of base S3 of this cotangent space. There is a nice pictorial way to describe these two, the connection between resolved conifold and deformed conifold. That is that well, if you have a T star of S3, well, you can think of you have a 3-sphere, And at each point, you have a cotangent space to it. And if you have a cotangent space to it, then you can consider two spheres that surround the origin of this cotangent space. So you have S3, and then you have some kind of S2 to it. But S3 has a finite radius. S2 can shrink to the base point of this cotangent space. So you can describe this geometry in this kind of model, where this direction corresponds to S3, and this direction corresponds to S2. And S3 has a finite radius given by the square root of mu. So if mu is non-zero, then you have a nice smooth cotangent space of S3. As mu goes to 0, S3 shrinks to a point, so you get some singular space. So that would be a conifold singularity. The resolved conifold, on the other hand, has a base CP1, which is of finite size. So in that case, the geometry would look like this. Now, S3's direction can shrink to a point, but S2 direction has a finite size, which is characterized by the scalar moduli. So this would be a resolved conifold. So these are connected to each other here in the limit of t equals 0, and here in the limit of mu equals 0. So I'd like to now describe a more general setup. So more generally, I would like to tell you, in the perhaps reminder of time, the construction of so-called toric Calabi-Yau. So in order to describe toric Calabi-Yau, we start with a geometry which is Cn plus 3 over 0. So for example, in these two examples, capital N would be 1. Okay, so you have n plus 1 complex coordinate. N plus 3 complex coordinate. And then you consider a natural scalar form for this flat space, which is given by dzi wedge dzi bar. And then, well, you want complex three-dimensional manifold in the end. So what you want to do is to gauge sum of the coordinate, to remove the sum of the coordinate by symmetry. So what you do is to introduce U1 to the N symmetry, which you may think of as some kind of gauge symmetry. So each Zi carries some U1 charge, which is given by Qi1, Qni, where this I goes from 1 to n plus 3. So basically what it does is that rotate Zi by a phase. Like that. And you treat this just as if it is a gauge symmetry. And in fact, you can translate this construction of toric Calabi-Yau manifold in the language of two-dimensional gauged linear sigma model. And there is a beautiful paper by, again, Ed Witten called Phases of N equal 2 Theories in 2 Dimensions. And as usual, I highly recommend this paper to you. And that's 9301042. And so basically, this toric procedure can be put in the language of gauge symmetry. So as gauge symmetry, you have a Gauss law constraint, which is given by this equation. Where T is going to be your scalar parameter, scalar moduli. And then you divide the locus, you divide the space of solution by U1 to the n. So as usual, gauge symmetry, each gauge symmetry kills twice. Once by Gauss law constraint, and the second time by dividing it by symmetry. So for each gauge symmetry removes one complex variable, so you land on 3 complex dimensional space. And this turned out to be Calabi-Yau if and only if sum of our charges is equal to 0 for each one of this U1 to the n gauge symmetry. So this is your Calabi-Yau condition. And as I said, all this can be formulated in the language of gauged linear sigma model in 2 dimensions. And so you have a nice 2-dimensional description of the whole thing. So let me give you some example. So for example, let's look at this local CP2 that we just talked about. So in this case, you have Z0, Z1, Z2, Z3 with symmetry e to the minus 3 I theta Z0, e to the I theta Z1, e to the I theta Z2, e to the I theta Z3. And then the Gauss law constraint you want to impose is minus 3 Z0 square plus Z1 square plus Z3 square, Z2 square plus Z3 square is equal to T. That would be your Gauss law constraint. So this is what you want to do. And the Kähler form would be equal to dzi over dzi bar. But it turns out that it is actually convenient to parameterize each zi is equal to square root of pi times e to the I theta. Oh, sorry, e to the I phi I. And there is a reason that I put this square root to it, because if I do that, this Kähler form takes this symplectic form. This phi direction is a torus direction, and p is a radius direction to it. So with this parameterization, this Gauss law constraint and gauge symmetry becomes particularly simple, because now in this polar coordinate, the gauge symmetry is phi 0, phi 1, phi 2, phi 3 is going to be phi 0 minus 3 theta, phi 1 plus theta, phi 2 plus theta, phi 3 plus theta. And then the Gauss law constraint is minus 3 p naught plus p1 plus p2 plus p3 is equal to t. So you can see that things are linearized here. So in particular, this means that we can remove phi naught, because you can always set theta to be the 1/3, third times phi naught. And we can remove p naught by this equation. So then we can get some kind of space of theta, phi 1, phi 2, phi 3, over space of p1, p2, p3. So let's try to describe the resulting space. Well, you get a space of phi 1, phi 2, phi 3 over space of p1, p2, p3. Phi 1, phi 2, phi 3 is a periodic, so it's like a coordinate on torus. So you get T3 fibration over space of P1, P2, P3. But what is the space of P1, P2, P3? Well, first of all these P1 has to be positive number because of this parameterization. And second of all, sum of this P1, P2, P3 has to be greater than T, because subtracting minus 3P, so that should give you T. So that means that P1, P2, P3 has to be positive. And also the sum of that should be greater than T. And well, in the 3-dimensional space of P1, P2, P3, well, first of all, you take the eighths of this total space by restricting them to be all positive. But then I have to remove the corner to it, because I require that sum of them should be greater than T. So the size of this space is parameterized by T. So it turns out that this space has a natural interpretation, because there is a T3 fibered over this space. And on the boundary, here, 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 one of the three cycles vanishes. Because remember that P is the size of this torus here. So on the boundary, one of the P's are 0, so one of the cycles degenerate. If you have a line here, on each one of these lines, 2 cycles degenerate. And on this corner, 3 cycles degenerate. And here, you have a base P1, P2. So therefore, this diagram captures the geometry of T3 fibration, and this is called toric diagram. So in Calabi-Yau literature, sometimes you hear about toric diagrams, and there is nothing mysterious about it. It's just this type of picture that shows the structure of T3 fibration. So now, given this tool, we can characterize other spaces. So basically what it says is that once you know the charge assignment, you can understand the geometry of Calabi-Yau. So for example, in the case of resolved conifold, we have a Q, which is given by -1, -1, +1, +1. So I leave it to your exercise to actually show that the resulting conifold toric diagram would be like this. And in the case of local CP2, local CP1 cross CP1, the Q is given by -2, 1, 1, 0, 0, -2, 0, 0, 1, 1. And again, I leave it to your exercise to figure out what the toric diagram is. Now, this is one way to present the toric Calabi-Yau manifold. There are other ways. So here we consider T3 fibration. But you can also present the toric Calabi-Yau as T2 times R fibration. And sometimes this type of presentation is useful. For example, if I have time later, I will discuss application of this. And in terms of topological vertex, etc. So now finally, I have maybe 5 minutes left, so I will briefly tell you about mirror symmetry for toric. So this was, there are earlier mathematical literature on that, but in the context of physical sigma model, this was done by Hori and Vafa in 0002222. And also there is a set of lecture notes summarized in a big book called Mirror Symmetry, and part 2 of that book gives you this description in more detail. But I just want to briefly remind you that if you have a pair of Calabi-Yau manifold, it's called a mirror pair. If A model on M is equivalent to B model on W. So suppose you have A model on toric Calabi-Yau, then you can ask what is a mirror Calabi-Yau manifold, and this construction gives you an answer to it. So the idea of Hori and Buffer is that now, thanks to the translation by Witten, that you can describe the sigma model with toric Calabi-Yau using the language of linear sigma model. So suppose M is given as toric Calabi-Yau with charge QIA and scalar moduli TA. Then what they did was actually they used T-duality transformation on fiber T3. So you have a T3 fibration. So for on each of this fiber, you can do T-duality transformation. But you have to be careful because sometimes fiber degenerate. And then there are instanton corrections associated to it, both X instantons. And if you take those into account, you find that the mirror Calabi-Yau manifold is given by equation in C4 given by the following equation. Where this function f is given by this type of thing, where this n, m, and c are given by these sets of constraints. So by solving these equations, you can find this function. So originally, Hori and Buffer derived this by using T-duality and instanton computation. More recently, there is actually a nice derivation of this mirror partner using language of D-brain. So I was actually planning to go into the discussion of D-brain today, but I ran out of time, so this will be tomorrow. But there is actually also a D-brain way of deriving this mirror pair, mirror partner. So for example, in the case of conifold, where Q is -1, -1, 1, 1, then the resulting F is given by this. So you can compute you can identify the mirror partner of the conifold. So you can reduce the instanton computation on the conifold A model to classical geometric computation in this mirror B model. Okay? So I think that this is a good time to stop, so I can pause and ask for any questions. Thank you.